Hello everyone, my name is Iago and in this video I will show you what I did on my robotics final project. I will explain to you what I did to implement a particle filter, who is also called Monte Carlo algorithm, and a mapping algorithm. Both of this code can be used to autonomous navigation, but it's not the goal of this project. So, to begin, in order to better understand what I did, let's understand a little bit more about the particle filters. A particle filter is a probabilistic algorithm who uses the map of the environment and the measurements coming from the sensor of the robots to try to predict where the robot is on the map. The more common name of this algorithm is a particle filter, but do you ever think about why particles? Why filter? So let me explain it using a 1D example. To start, let's consider my rule. It's a drone who can measure the distance from the ground using a laser. My drone knows the map of the environment and also keeps the same altitude and has a perfect model of his dynamics behavior. My drone starts to fly on this point. So, how can I know the pose of this drone using only the distance from the ground? Yes, I can do it, but I can use a Monte Carlo algorithm in order to estimate the pose after some seconds. First, I estimate some particles. We are on the beginning of the algorithm, so we use a uniform distribution in order to put the particles all around the map. As you can see, I have a lot of estimated positions at this time. Now it's time to take some measurements. The first one, who is my reference, is a real measurement coming from the drone. The other measurement is an assumption. If the drone was on the particle position, what will be the measurement coming from the drone? Now, using this vector containing all the measurements, we can put some weight in each particle. A weight is how near the measurement coming from the particle is from the measurement coming from the drone. As you can see, if the particle is more near of the measurement coming from the drone, that particle has more weight. Now, using the weight calculated on the last interaction, we do again the distribution of the particles around the map. But this time we do this in a different way. But now, instead to do a random distribution, we use a weight of each particles calculated on the last interaction to calculate the chance of the particle be near of that position. As you can see, the new particles are redistributed around the more weighted particles, and when the distance from the ground is very different from the measurement come from the drone, there is no particles remaining. The drone keeps moving, so we have to move the particles on the same direction of the drone. We use the model in order to do it. Now we are ready to run the algorithm again. We take some measurements of the particles and the drone. We calculate the weight of each particle and then put the particle on the map again. This algorithm is a recursive algorithm, so we have to do it over and over again if we want to keep updating the position of the drone. The measurements of this algorithm is a vector containing all the particles. And the measurement predicted of this algorithm is an average calculated from that vector. As I said on the beginning, we need a map in order to estimate the position of the robot. We can obtain this map using the ROSG mapping package. As you can see now, we have a robot with a lidar moving on the map. The mapping algorithm is capturing the measurements coming from the drone and transforming it on a map. Now, we can save the map obtained using the Gmap algorithm in order to use it on our localization algorithm. To save it, we just have to pick the information inside the /map node and save it as a YALM file. Now it's time to run our tests. First of all, we start to move the robot around the map to see the particles conversion to the right position of the robot. Then, we pick the robot and put on the random position on the map. In this case, we are running on a symmetrical map provided by the TurtleBot free package. This map shows one of the biggest limitations of this algorithm. If the robot has two or more similar positions on the map where the measurements it's almost the same, the algorithm maybe can converge for a wrong position and give the wrong orientation of the robot.